Okay, I'll pick it. So, my name is Ayman. And this is our presentation of our course at PSA and Wilkes. This is the table of contents of our presentation. First is the program overview, then we'll talk about the PSA job shadowing and AI learning plus tools, which we did in the earlier weeks at Wilkes. Then sensors and decisions, which is also at Wilkes. And then after that, we'll learn about what we did at PSA with drone software. And then we'll come back to Wilkes for robot assembly, maze and line algorithms, and then we'll talk about warehouse things that we did. So to start, like an overview of the program, it was just a split days between Wilkes and PSA. And at PSA we did job shadowing and learned about what the company does and stuff, and more so manufacturing and like some engineering things, more real world examples. And then at Wilkes we worked on actual projects and new like challenges and stuff every day. The format of the program was Mondays and Tuesdays we spent at PSA. We would learn about automation, manufacturing, machine systems, and like Caleb just said, job shadowing. And then Wednesdays and Thursdays we'd spend at Wilkes, which was a dual enrollment college class, and we get 3 credits towards most universities if they accept it. And we'd spend our days learning about circuits, sensors, AI tools, robot coding, and testing. And every Thursday we would have a competition, and anybody could compete in it, and usually there'd be a task like having your robot follow this line, come to this like this like end zone, and then turn around, and then basically whoever had the most robust system would get the award. So one of the first projects we did was we worked with prompting with AI and using it for research and stuff, like properly. So we used, most people use Claude, and we practiced like talking to it and like structuring prompts better to get certain things and giving it tasks and how to use it, how to use LLMs more efficiently. And then in the first week at Wilkes, we started, you could do it, I'll do them all. Okay. Training AI to recognize imaging sounds. So we had this house robot, which is basically a pre-built robot that had a camera robot, like it was a robot with wheels, and it had 2 wheels and like a roller on the front, so it was more stable. But the purpose of it was to like make the coding more accessible and understandable. So at the top there, it shows some of the block coding, which is different from like real code. It's just formatted differently, so it's like puzzle pieces that you can fit together. We did image training and sound recognition, but the robot could respond to image and sound recognition. So we have like traffic signs on the ground, and then it'd be a stop sign, a horn, and turn right, and then basically it should be able to recognize it and then do the corresponding action. And then, so yeah, for like the image recognition and sound recognition, the software where we did the block coding had like a feature where you could make a little AI model, so you just like upload some images and train it, and then it could recognize the images. But it was like okay, but we wanted to do something more, so we kind of did some compute offloading and used Google's data centers through Teachable Machine, and we inputted like thousands of images and then ran a bunch of epochs, it's called, in training cycles, and we made our own custom image model, which you saw in that video, and we linked that to the robot using a like code, and then we got it to run that model, so it's smarter. Oh yeah. So our first like couple days at PSA, we just did a tour. So we walked around and saw the facility, and they showed us how everything's done, how they make machines. We weren't allowed to take any pictures really, because there's a lot of secret stuff. But it was really neat. They showed us these robotic arms and stuff they had, and how they work with like parts and build things and all their manufacturing machines. Also earlier in the program, at most rather than PSA, we focused on breadboards and microcontrollers. For example, in the picture, it's an Arduino, which basically has a bunch of like resistors, header pins, different electrical components that allows it to store code and run it on its own when it's connected to power. We had a lot of circuits with sensors to replicate AI robots, like the future robot that we had the Pico 4-wheel drive. So before doing that, we imitated the sensors and systems they had with like simple elementary components like push buttons, LEDs, and photocell sensors. And then we also kept all that evidence in tables to like mimic AI training, like early in the program.
So one of our earlier circuits was a line tracking circuit. I know other people kind of cover this a lot, but it's just we were working with a breadboard and wiring things, and we used a photocell, so it just senses. So the more light that comes in, it varies the voltage that goes out, and then we can use that to go to an LED so it goes brighter, and just kind of mimicked how the line tracking would work.
One of the earlier projects we did, which was around halfway, we did a plant needs water system, which a lot of people have already covered, but we had soil in a cup and two ends of a circuit, which would be positive and negative, in a coil wrapped around the nail, and then we put it on the same side of the cup because if you put it on different locations for each test, then the results wouldn't be as accurate. And then the soil, which is completely dry, isn't totally not conductive, but has a little bit of conduction. And then basically the closer the probes are, the higher conduction it has. But obviously that isn't the main value of it. But the more water there is, the more conductive it is because water doesn't have as much resistance. It's like wire, and it's, imagine the soil would be the air, and then the water would be a wire. It helps connect the two probes, and based on the resistance, it would show the voltage, and the voltage would go to like an LED or a multimeter to show how much water there was.
So another circuit we did, see in the video, is we used the Arduino microcontroller, and we just hooked up the push button circuit to it, but we also connected it to, like, we actually wrote code on it so we could get output, but you could see it in this next one.
This is the code we did. We used Arduino IDE. We wrote basic code that allowed the LED to like react to the buttons. You can see these LSIFs and the structure of the Arduino code. It's different from the Tanya IDE and the MicroPython, but it printed the readings to serial monitors so we could have like similar to the robot. The robot could have different values that we could use for testing and debugging.
Yeah, and then so like every time you press a button, it would say like left button pressed, other one is not pressed, just to print that out on the computer. So when we made these circuits, we'd make like tons of tables and charts to record the data, and kind of like when you're doing just like a science experiment, and then you just compare the results. But we did this for everything, all the projects really. We had to make like tables and record everything, and then see how accurate it was and how well it worked.
On the PSA side, we learned about drone software, MATLAB, and Linux tools. We didn't directly do the MATLAB software because I don't think we had the computers yet. So we used MATLAB on-ramp, which is the course to learn the basics. And we also were given laptops to download, or not download, but run Linux like temporarily on the drive. And we also use software like eCalc, which would help us like simulate drones or different components to find like the best fit for whatever we wanted. And for Linux, it was good because a lot of engineering software is made for Linux, like keydown control that many people have talked about already.
Yeah. First out of 57 Ti. We did drone work, so we took them apart, some like dummy drones, we saw how everything worked. We learned about how the GPS works, we used the software, and then we saw a test flight, and
Building the Pico four-wheel drive robot, obviously I talked about it before, but it's this robot, it came in a kit like that, and we had to assemble everything, and like, it started out as that, and we said that we got it to look like that as the finished project. It came with a manual, it came with a microcontroller, which is the Raspberry Pi Pico, it had Wi-Fi and Bluetooth, and it came with a grayscale sensor, RGB lights, a photo interrupter, which is basically like, it's like a laser on like two sides, and if something goes in front of it, then it detects that, and it would basically be able to tell the speed as it would be inside of the robot, and it would be like between an encoder, which was attached to the motor, and an encoder is just like a wheel with holes in it. And we tested the car's basic movement before we like actually started doing the other projects, so just going forward and right and left.
So initially after we assembled it, we just got started with getting it to move and stuff and writing some basic code into the robot, and that worked well.
Later in the PSA, since we switched halfway through, it's in a different order than the other group, we learned about HMIs, PLCs, and ladder logic. A PLC is a programmable logic controller that reads inputs, runs logic, and controls outputs. And an HMI is a human machine interface, which basically converts what the PLC's inputs and outputs are in a way that people can read it, control it. And you can see on the bottom, it's like a screen with controls and the stop button up top. And we also learned about ladder logic, which is a way to program things that like machines and stuff. And it turns the digital logic to and false signals, and we practice that handwritten first.
We also did some stuff with pneumatics, so air, instead of like electricity and things powering, it was like air pressure, controlling cylinders and stuff. We learned about a pool liner machine that they made a while ago and how that worked. And then we learned about a lot of production processes like different parts and water bottles as an example, and how the systems work.
Later on in the Wilkes, we finally got to obstacle avoidance and like going through this maze as you see right in front of us. And it would have an ultrasonic sensor attached to a servo with like a plastic bracket and screws. It would have stop and turn avoidance at first, which was our first assignment. So it would drive when nothing's in front of it. If something's right next to it, it would back up, turn one way, and then try again. And then if that didn't work, it would turn a different direction. But we didn't have it move on the servo just yet. And next we did basic maze navigation, which means it would scan left and right, then turn towards the side with more open space. It would be just a simple greater than or less than if statement. And then our robot used an AI algorithm that we were given to in a packet, and then we were able to read it to since it was beginner friendly. But basically the ultrasonic sensor, I know other people talked about it, but just like add on to it, it's two little like probes with like a grate on it, and it sends ultrasonic signals, which is just sound, but obviously we can't hear it. But it would send a signal towards the wall and then wait for it to come back, and then based on how long it took, or if it didn't get it at all, it would be able to see the distance and also know whether or not there was something in front of it. But obviously that only works straight ahead, so this servo would look left and right, and then it would basically be able to see all around it.
Then we did the line following stuff. So this was pretty simple. It's just like there's three sensors on the bottom of the robot, and if it sees the line on this one, then it's gonna move to the middle one, and vice versa. But another challenge that was added on to that we did was, you saw in that video, it should also follow the line, but then once it hits an obstacle, it goes around it. So the way I did that is it just hits the obstacle, then turns left, then right. But when it turns right, it goes on an angle and keeps looking until it catches back on the line. And then we had that integrate with our like delivery mock-up system, so it would start and then stop and go around, then to the end, then turn around and stop.
The next, like one of our final projects we had with the line following was before the obstacle one, but after the like simple line following. Is as you can see on top, it would start at the start marker, then it follow the line until it goes to the 000, which means that it's like just a full black line, which means like it's signaling to the robot that it's no longer just on a thin line, it's on the delivery marker, and then it would pause, do a full 180, and then follow the line back, and either stop there or go back. It's basically mocking a package in like a warehouse, but we didn't really have a package because there was no hardware to drop it off or do anything. But it was just an idea. At the bottom left is an example of what the Donnie IDE looked like. It was MicroPython, and it's pretty similar to Arduino IDE, except just like different syntax, which is like basically a different language. Right?
Python.
Yeah, it's like the difference between like English and Spanish. It's still the same, similar base, but it's just you can't say the same words. Yeah, it combined line following, market detection, and testing. So it was building off of the previous.
So what the Pico card taught us, we learned a lot about just movement commands and a lot about decision making and making things right. Because it was hard working on the code for a lot of the autonomous stuff because you could hard code it to okay it goes left then it goes right here, but to make it make its own decisions, that was hard. Especially when like the sonar panning left and right, so it shoots. I mean, how I did it was you have to shoot. It pans left and right at 8 different angles, and then it shoots the signal back at 8 different angles, and then it catches all of them and stores it in a variable, and then it calls upon that variable after it did its full sweep, and then it makes its decision. So that was just a lot of hard logic, but it was neat seeing how we could use code and interact it with physical hardware and stuff, and especially just the autonomous stuff was neat. Yeah, it was neat having challenges. Me and Ayman would always race our robots, and I used to win, but not anymore. He's faster now, but yeah, and then we did other challenges and stuff, and it was neat.
Lastly, I know it's like it was just a bunch of the robot stuff, but back to the PSA. For our final week, we learned about electrical engineering with Chris because I'm pretty sure he's busy. So we spent only the last week with Chris. Examples are on the right are this one electrical engineering schematics, which this one uses ladder logic, which is what we learned about before. And the other ones are just more complex. They look pretty similar to the one on the right. He showed us real-world examples of like actual schematics and blueprints that PSA uses or has already used, and then we had a packet, and we were also able to like.
So overall summary, we found out that when we used AI, it works best when you actually oversee it and stuff. This is a cool video. Did my car, by the way. We learned about sensors and how they work with like code and stuff. That was difficult. It's a lot harder to link things like sonar and stuff to code than you would think. There's a lot of configuration stuff and getting things right. And then there's a lot of variation. Like my car may turn at a slightly different angle than Ayman's, so we can't have the same code. You have to keep testing. And that's like part of good engineering, it's lots of testing. But yeah, otherwise it was a fun project, fun course. I think this is good. Yeah, any questions?
Any questions for Ayman?